Hello everyone. Yesterday actually I was trying to get the Visual Studio up and running how um, Karpati sir has been doing, so I missed to record the video. So means mostly it was just recreating what I did in the um, Jupyter notebook. Few of the things just you need to take care of. I think it should be easier and simpler to do that. Just let me know if you all find it tough to uh, recreate that, right? I can help, or I can see if I can create again with that. So I completed near about um I think, yeah, so till here I have done 122. Now I'm going to look at the multi-headed self-attention. Let's get started.
Okay, so now we've implemented the scale.product attention. Now next up in the attention is all you need paper. There's something called multi-head attention. And what is multi-head attention? It's just applying multiple attentions in parallel and concatenating the results. So they have a little bit of diagram here. I don't know if this is super clear. It's really just multiple attentions in parallel. So let's implement that. Fairly straightforward. If we want a multi-head attention, then we want multiple heads of self-attention running in parallel. So in PyTorch, we can do this by simply creating multiple heads. So however many heads you want, and then what is the head size of each.
And what head is the one that takes key query value pair, calculates the weight, um, if you see in the paper, one is the query that it is looking for. The next is the key, how it um represents itself. That was the notion behind it. And then what it wants to project, that is the V. Okay, that was here. All of them give a head size vector. Do a dot product. Um, we take the positional. It's the positional. Okay, so for each of the we take the token embedding and positional embedding as well, add them up, and that's where it's also first we start with self attention. So we pull that, give that to the self attention layer, which does, where is the self attention head? It does this multiplication and everything and returns an output. We calculate the softmax. What will be the size of this? I just want to take the size. All will return BT into its size. It will return. All of them will return. Um, okay, and here also BT. BT head size, and this will be equal to head size. Trail will do a T T. Okay. From the diagonal and downward sides, all will be one here. Okay. And coda block. This will be commented as we all the nodes to talk to each other for it. And then now does torch dot once want to no, that's what. So diagonal and under this all of them are one. Then wherever the trill is 0, fill it with minus infinity. So the top that will become minus infinity, just to specify that, so that all the elements it sees all the preceding element rather than the afterwards element. Okay, right? Means this element or this element in the context of this element in the context of these two, this element in the context of this, it doesn't seize whatever comes afterwards, because in text generation, uh, we try to predict the future elements, right? In something like sentiment analysis or everything, we should have the authority to see all of them and then make a sentiment. So in that case, it won't be zeros in sentiment analysis, but here, 0. Then it does the softmax and everything to calculate the weights of that. Then with the value, it tries to do a dot product. Okay, so that's forward each of the head, which is kind of specifying that my correlation with the other elements is what we are getting out of here. It's each of the element that is sitting here, right? What is its correlation with this element, something like that. That's what is happening in the head. So it's majorly. So once we have the token embedding and the position where it belongs to, right? We add that, and for each of those, what is the correlation with the other elements in that? That comes here. Soft max. So it will be B for each T, and head size it should have been, yeah. It should have been, oh, that is for each of the blocks, okay. So we'll get bt into t out of this, right? B, T, T, when this dot product happens. So for each block size, um, so for each block size, token one, as we were taking examples here, right? Like this example we were taking, right? So 24 has no context, so it will have its own value. Then 43 in correlation with 24, 58 with 43 and 24, 5 with 58, 43, 24. That's what is happening there. Once it gets that, no, it's not chill. It's not. Most fill it does that for every block, for every, that's what, and then here it will be B T. Now I understand why he was writing what it gives, and V is BT into head size. When we multiply, V will be there, T into head size. Okay. Let me print it. What is happening with the dot product is V and this is V, V. Initially, we are telling on the first element that will come, right? The first element that will come will take the value as it is. Okay, so that takes minus this whatever it is, because all of them are zeros. Should have been minus infinity now. Oh, I did the softmax. Okay. Then next we are telling no, now we have this element has correlation with this one. So this gets multiplied by this. Oh, sorry. It's a bit tough, but for every token we have a head size that talks about or that encapsulates token has a head size length this thing that encapsulates the information of its correlation with the other elements in there. Anyway, later, right? In the first instance, let's just go through it one by one. Again, when we'll go through it, right, we'll see how what intuition we can make out of it. So that was self-attention. Now he's going to multi-head attention. Head attention is fine. Sorry. Oh, that was nicer. Whatever it did, but looks like did a good job. So multi-headed attention. So for each of the head, uh, we need the head size and then the number of heads. Head size, module list, and everything. Now we are not crunching that too. This is not happening, I think. And then in the forward pass, so we are concatenating the output that we are getting. When we do an head of X, we are getting BT head size, BT head size, BT head size. So from each of the heads, we are getting BT head size, BT head size, BT head size, and concatenate across the minus one. I think then it will be BT head size into a number of heads. Okay, so it is something like So it is something like oops, sorry. This is B, this is T, this is head size. We have one more like this, one more like this, okay, like this. The last I mentioned it is concatenated across this, so I think this will be here. The next ones will sit on top of this. So here as we have 10, 7, 4, 1, 22, 19, 16, 13, like that. Another one that will be have, let's say in that there is 11, 8, 5, 2 in place of this, right? We have one more next to that. Like here we have 22, 19, 16, 13. There it will be say 23, 22, 18, 14. Okay, like that. So the 11, 8, 5, 2 that we have right here will sit on top of this. So 10, 7, 4, 1, 11, 8, 5, 2, like that. The other block that is there next to it will sit on top of this. So 22, 19, 16, 13, that will be 23, 22, 18, 14, whatever I saw. So they will stack on top of that. So I believe this should be T, yeah. So head size into number of heads.
And then we run all of them in parallel into a list and simply concatenate all of the outputs. And we're concatenating over the channel dimension. So the way this looks now is we don't have just a single attention that has a hit size of 32, because remember, n embed is 32.
So here rather than that, what we are doing is multi-headed attention, a number of heads he's saying is 4, and the head size number of embedding is 32. So what he's saying, each head size should be 8, so that when this concatenation happens, right, this head size into n heads happens, we get 32 itself. Okay, so 8 heads each of, no, 4 heads each of size 8. Okay, 4 heads each of size 8, and that multiplies to get 32 here again.
Instead of having one communication channel, we now have 4 communication channels in parallel. And each one of these communication channels typically will be smaller correspondingly. So because we have 4 communication channels, we want 8-dimensional self-attention. And so from each communication channel, we're getting together 8-dimensional vectors, and then we have 4 of them, and that concatenates to give us 32, which
That's what I explained here, right? 8, 8, 8, 8 will sit on top of that here, right? So somehow this should be 8, one more 8, the next one 8, 8, 8, so like that 4 8, so 32.
is the original n embed. And so this is kind of similar to, if you're familiar with convolutions, this is kind of like a group convolution, because basically, instead of having one large convolution, we do convolution in groups, and that's multi-headed self-attention. And so then here we just use SA heads, self-attention heads instead. Now I actually ran it, and scrolling down, I ran the same thing, and then we now get this down to 2.28.
राज सोवे सा कानन कुंडल कुंचित की. How he does the evaluation here? Um, Nandana Japatapa Mahajagavandana. He's doing it both on validation and everything, is it? Wait.
roughly. And the output is still, the generation is still not amazing, but clearly the validation loss is improving because we were at 2.4 just now. And so it helps to have multiple communication channels because obviously these tokens have a lot to talk about. They want to find the consonants, the vowels, they want to find the vowels just from certain positions, they want to find any kinds of different things. And so it helps to create multiple independent channels of communication, gather lots of different types of data, and then decode the output.
One thing, estimate loss. Estimate loss, I think I wrote. Estimate losses here. It is telling not to. Model is in evaluation phase. Split. जब नाम सुनावे से रोग हरे सब पीड़ा निरंतर हनुमत वीरा हनुमान गोसाई भजन ध्यान जो लाए. सूराजा के काज सकल तुम साजा मनोरथ जो को नित्य जीवन फल पावे जो करता. So if you are understanding what is happening here, right? First is it has told Torch do not keep track of the gradients, and evaluation also, when we set it, we're in the evaluation mode, and we are not going to call the backprop. It doesn't keep track of multiple things. As a result, it's a bit more faster and much more efficient. So we have train and validation losses. We are initializing an array with zeros where we'll store. Now first we are going through the training. We are calculating, so we are calculating the loss. We are storing the loss for all of those batches. Evaluation iteration, we need to specify how much we want to do. And calculates the loss. Then we mean it up, and then we do it for the validation as well. Then for each batch we calculate the mean loss for all the batches. Okay, let me run this. Actually, it's Sita Sasagam Teachera Amna Tahida. How come it is evaluating? So G is the model. Sorry for naming that way. G G evaluation after each training is just doing that. So what's happening is whenever the model get trained here, right? We're again estimating loss based on so we are again calculating a bit of loss for different batch sizes and then meaning it out just to show means how much is near about. So initially if you see the train loss, right, it is 4.2103 and the validation loss is kind of nearly the same, and that's the data it hasn't seen yet, the validation loss. We'll let it run and see here.
Now, going back to the paper for a second, of course, I didn't explain this figure in full detail, but we are starting to see some components of what we've already implemented. We have the positional encodings, the token encodings that add, we have the masked multi-headed attention implemented. Now, here's another multi-headed attention, which is a cross attention to an encoder, which we're not going to implement in this case. I'm going to come back to that later. But I want you to notice that there's a feed forward part here, and then this is grouped into a block that gets repeated again and again. Now the feed forward part here is just a simple multi-layer perceptron. So the multi-headed, so here position-wise feed forward networks is just a simple little MLP. So I want to start basically in a similar fashion, also adding computation into the network. And this computation is on a per node level. So I've already implemented it, and you can see the diff highlighted on the left here when I've added or changed things.
So in feed forward, we are defining a linear layer and embeddings and outputs and an embedding. I think that is for each of the batch, each of the token 32 length, and then we are doing a ReLU, which is a non-linear function. Multi-headed, headed, good. It generates a good amount of code here. Sonnet, we are defining it sequential. Here he's defining it something like a jello. I'm not sure what is that. Review it happened and see, barely I had to write code. So okay, this anyway went through it. And after multi-headed attention, he has added. After this, he has added self dot feed forward equal to feed forward and what it takes. What is the fan in fan out of the linear layer, right? Two 2.23 or something previously. How much we are getting? 2.27. Oh no. Yeah, in the validation it is 2.23. And it reduced a bit.
I've already implemented it, and you can see the diff highlighted on the left here when I've added or changed things. Now, before we had
Actually, after going through this, right, we should code it on our own also once, just to get the understanding of it.
the multi-headed self-attention that did the communication, but we went way too fast to calculate the logits. So the tokens looked at each other, but didn't really have a lot of time to think on what they found from the other tokens. And so what I've implemented here is a little feed-forward single layer. And this little layer is just a linear followed by a ReLU nonlinearity, and that's it. So it's just a little layer. And then I call it feed-forward, an embed. And then this feed forward is just called sequentially right after the self-attention. So we self-attend, then we feed forward. And you'll notice that the feed forward here, when it's applying linear, this is on a per token level. All the tokens do this independently. So the self-attention is the communication, and then once they've gathered all the data, now they need to think on that data individually. And so that's what feed forward is doing, and that's why I've added it here. Now, when I train this, the validation loss actually continues to go down, now to 2.24, which is down from 2.28. The outputs still look kind of terrible, but at least we've improved the situation. And so as a preview, we're going to now start to intersperse the communication with the computation. And that's also what the transformer does when it has blocks that communicate and then compute, and it groups them and replicates them. Okay, so let me show you what we like to do. We'd like to do something like this. We have a block, and this block is basically this part here, except for the cross attention. Now the block basically intersperses communication and then computation. The communication is done using multi-headed self-attention, and then the computation is done using a feed-forward network on all the tokens independently. Now, what I've added here also is, you'll notice, this takes the number of embeddings in the embedding dimension and the number of heads that we would like, which is kind of like group size in group convolution. And I'm saying that the number of heads we'd like is 4.
This for sure we need to code again. Anyway, that's how you learn, right? I'm relying a lot on. So each block will have an underscore embedding, an underscore head, and here we need to initialize score embedding by number of heads so that at the end we get 32 size. Multi-headed attention, and we could have done like this as well. That would be that way. Oh no, oh yeah, it's an embedding. No, this is number of heads, right? Number of heads. It's that piling up of, right, 32. So 8, 8, 8, 8. 4 heads we need, and each of them are learning something from the other words. Attention, self-attention. Return X. And this block, uh, these all are not required, right? So in place of this, rather than having one single head and forward, we are doing multiples of these. So self dot blocks not sequential and an embedding and number of heads. So we have when we are going through this, right? So in place of again doing this, right, we will do self dot block x. 3 times it is going through. They're not happening parallelly, they're sequential, one after the other.
And so because this is 32, we calculate that because this is 32, the number of heads should be 4, the head size should be 8, so that everything sort of works out channel-wise. So this is how the transformer structures sort of the sizes, typically. So the head size will become 8, and then this is how we want to intersperse them. And then here, I'm trying to create blocks, which is just a sequential application of block, block, block. So that we're interspersing communication feedforward many, many times, and then finally we decode. Now, I actually tried to run this, and the problem is this doesn't actually give a very good answer, and a very good result. And the reason for that is we're starting to actually get like a pretty deep neural net. And deep neural nets suffer from optimization issues, and I think that's what we're kind of like slightly starting to run into. So we need one more idea that we can borrow from the transformer paper to resolve those difficulties. Now, there are two optimizations that dramatically help with the depth of these networks and make sure that the networks remain optimizable. Let's talk about the first one. The first one in this diagram is you see this arrow here, and then this arrow and this arrow. Those are skip connections, or sometimes called residual connections. They come from this paper, the Procedural Learning for Image Recognition, from about 2015, that introduced the concept. Now, these are basically, what it means is you transform the data, but then you have a skip connection with addition from the previous features. Now, the way I like to visualize it, that I prefer, is the following. Here the computation happens from the top to bottom, and basically you have this residual pathway, and you are free to fork off from the residual pathway, perform some computation, and then project back to the residual pathway via addition. And so you go from the inputs to the targets only via plus and plus and plus. And the reason this is useful is because during backpropagation, remember from our micrograd video earlier, addition distributes gradients equally to both of its branches that fed as the input. And so the supervision, or the gradients from the loss, basically hop through every addition node all the way to the input, and then also fork off into the residual blocks. But basically you have this gradient superhighway that goes directly from the supervision all the way to the input, unimpeded. And then these residual blocks are usually initialized in the beginning, so they contribute very, very little, if anything, to the residual pathway. They are initialized that way. So in the beginning, they are sort of almost kind of like not there. But then during the optimization, they come online over time, and they start to contribute. But at least at the initialization, you can go from directly supervision to the input. Gradient is unimpeded and just flows, and then the blocks over time kick in. And so that dramatically helps with the optimization. So let's implement this. So coming back to our block here, basically what we want to do is we want to do x equals x plus self-attention and x equals x plus self.feedforward. So this is x, and then we fork off and do some communication and come back. And we fork off and we do some computation and come back. So those are residual connections. And then swinging back up here, we also have to introduce this projection. So nn.linear, and this is going to be from after we concatenate this is the size n embed. So this is the output of the self-attention itself, but then we actually want the to apply the projection, and that's the
two places that addition happens. One is at this level, self each block tension and feed forward. That residual block coming into the picture. This is one thing understood. What was the what was the other? Where is the architecture? So here it gets put in here. That is happening. That's what we did from self-attention and forward. That happened. We don't have as of now this, and this. So we passed on that. And also during this, he's saying here also is talking about the projections. Multi-headed attention. It has different heads. Concatenation is happening and then moving to the linear layer. But here, oh, oh, we missed this part, is it? Okay. So he's implementing this linear part. I think we missed multi-headed attention. Okay. And
result. So the projection is just a linear transformation of the outcome of this layer. So that's the projection back into the residual pathway. And then here in the feed forward, it's going to be the same thing. I could have a self-dot projection here as well, but let me just simplify it and let me couple it inside the same sequential.
we did to the multi-headed this thing. It's everywhere we add a projection. Block has, oh, across block also it is going that way, is it? I don't think so. So block is this thing. There's nothing that comes here. Okay, so everything is inside block. So that's where nothing means with block we are doing anything. Okay, nothing x plus block is nothing x plus block is happening here. Okay, that is one thing. In the block now we have self attention and everything. Self attention and feed forward. self attention and feed forward. This is the one, but internal to the self attention. So everywhere there is a residual, and it will, and here as well. Here we don't have anything as of now.
Container. And so this is the projection layer going back into the residual pathway. And so that's it. So now we can train this. So I implemented one more small change. When you look into the paper again, you see that the dimensionality of input and output is 512 for them. And they're saying that the inner layer here in the feed forward has dimensionality of 2048. So there's a multiplier of 4. And so the inner layer of the feed forward network should be multiplied by 4 in terms of channel sizes. So I came here and I multiplied 4 times embed here for the feed forward, and then from 4 times n embed coming back down to n embed when we go back to the projection. So adding a bit of
That is not residual, that is just the projection that we are doing. Projection means um, internally we can have as big that heads and the output coming out, but we want at the end to come as an embedding. That's the main reason. I don't think this is anything to do with the residual here. Means in the neural networks, if you see, right, internally there are multiple layers that are coming in, but at the end what we want is it should be also, if we have implemented here, right, nh, see we how whatever we do initially, right, at the end we add a linear where whatever be the number of hidden layers, we want the output in terms of the vocab size. The same thing he's doing here as well. So how much ever input was there, we want the output to be in terms of an embedding. That's it. So it's just a projection. It has nothing to do with the residual, I believe. Yeah. And the same here as well. So he was saying here again, into these many number of channels we want, and at the end how much ever the internally the channels were, I want the output to be in terms of an embedding.
computation here and growing that layer that is in the residual block on the side of the residual pathway. And then I train this, and we actually get down all the way to 2.08.
All happening in the side way, right? So that picture that he was showing. So here, so it is going, X is going that way, that residual path, but apart from that, whatever is happening in the side, right? That's what it is here. And if we train the model,
validation loss. And we also see that the network is starting to get big enough that our train loss is getting ahead of validation loss. So we start to see like a little bit of overfitting. And our generations here are still not amazing, but at least you see that we can see like is here, this now, grieve sync. Like this starts to almost look like English. So yeah, we're starting to really get there. Okay, and the second innovation that is very helpful for optimizing very deep neural networks is right here. So we have this addition now, that's the residual part. But this norm is referring to something called layer norm. So layer norm is implemented in PyTorch. It's a paper that came out a while back here. And layer norm is very, very similar to bash norm. So remember back to our makemore series part 3. We implemented bash normalization. And bash normalization basically just made sure that across the bash dimension, any individual neuron had unit Gaussian distribution. So it was 0 mean and unit standard deviation, 1 standard deviation output. So what I did here is I'm copy pasting the bash norm 1D that we developed in our makemore series. And see here we can initialize, for example, this module, and we can have a batch of 32 100-dimensional vectors feeding through the bash norm layer. So what this does is it guarantees that when we look at just the 0th column, it's a 0 mean, 1 standard deviation. So it's normalizing every single column of this input. Now the rows are not going to be normalized by default, because we're just normalizing columns. So let's now implement layer norm. It's very complicated. Look, we come here, we change this from 0 to 1. So we don't normalize the columns, we normalize the rows.
Each of the batch.
And now we've implemented layer norm. So now the columns are not going to be normalized, but the rows are going to be normalized. For every individual example, its 100-dimensional vector is normalized in this way. And because our computation now does not span across examples, we can delete all of this buffers stuff because we can always apply this operation and don't need to maintain any running buffers. So we don't need the buffers. There's no distinction between training and test time. And we don't need these running buffers.
Let's do it in the next video. Hopefully we are seeing, so in the fourth iteration 2.07 we see somewhat a loss here. If you want, I can put it in there, or in the next video we'll just see how much loss we received. But let's cap it up here. We, I think, covered 13 minutes of the video, but it's already an hour or so. But we have few more to cover. I think 20 minutes. We'll go through the layer norm in the next iteration. Thank you.